So here's where we're going to start to get a little bit more detail about the in the intestines, right? As far as some of the differences. So where we had just finished up in the previous video, and I apologize, I had a little glitch. I had to pause that one and ended up ending it. Anyways, I'm still figuring out this program, but some of the differences, right, within the duodenum. Remember, the duodenum secretes cholecystokinin and something called secretin. This is how the pancreas knows to release lipase, amylase, trypsin, bicarbonate, right? Because as the duodenum stretches and distends, that stimulates the pancreas to release these different hormones. So because of the chyme, right down here, some of the structures that we see within the duodenum are these Brunner's glands. These Brunner's glands can also be called duodenal glands. Right? Why? Because they are located within the duodenum. They produce a tremendous amount of mucus. That mucus helps to counteract or essentially protect the duodenal wall from the acidic chyme. You don't see these Brunner's glands throughout the intestine. Right? You see them in the duodenum. By the time that the chyme has made it from the duodenum down through and has entered into the second part of the small intestine, being the jejunum, right, into the third part of the small intestine, being the ileum, the pH of the chyme, the pH of that acidic, that slurried food is no longer acidic, so we don't need to have this immense protective mucus layer any longer. These things here, these really big, tall, large fingers, these are called plica circulae or plica circularis. It's just a fancy word for circular folds. Right? These are seen throughout the intestine, right? From the duodenum, the jejunum, the ileum, they're seen throughout. However, they are much more pronounced in the jejunum. Again, that second portion of the small intestine. These folds, right, these plica circularis, these are gigantic. Right? I mean, this fold here, this is not a villi. This is a circular fold. This, like in your own intestines, you would be able to measure with a tape, with a ruler. Right? These are large enough that you can actually grab a hold of them with your finger. They're tremendously large. Oops. Right? They are tremendously large. The whole reason they exist is to increase the surface area of the intestines. Right? Think of it. The intestinal wall. Well, if these plica circularis didn't exist, right, the intestinal wall would just simply go straight across. So you'd only have, call it from here to here, call that 6 inches. So you would only have enough villi that would be able to fit in this 6 inches. But with these circular folds, if I were to measure the length of the intestinal wall, I mean, I go up inch, 2, 3, 4, 5, 6 inches, 7 inches, 8 inches, 9. So you get my point, so on and so forth. So those circular folds, or those plica circularis, significantly increase the surface area potential. And how it does that is because it allows for significantly greater number of villi. The villi contain enormous numbers of microvilli. So again, the combination of the three dramatically increases the absorptive capacity of the intestine. Now these things here, what are called Peyer's patches. We see large nodules of lymphoid tissue. They're kind of like lymph nodes, so they just don't have a capsule. Right? We see lymphoid tissue throughout the small intestine. Right? We've all heard of, we've all seen those Activia commercials, the yogurt commercial. Jamie Lee Curtis comes on, it's like, ugh, not feeling so regular, huh? Have some yogurt, it'll help. Right? What is true about that is, yes, certain strains of bacteria absolutely help benefit the intestinal flora. However, a cup of Activia is like throwing a marble into a pool. Is it going to make a ripple? Yep. Is it going to make any appreciable difference? Not in the least. Right? the number of colonized bacteria in the intestines are in the many, many billions, if not trillions. Most cups of yogurt have tens of millions, right? The highest ones might have, might be the hundreds of millions, but generally not much higher than that. So it's not nearly high enough to be a therapeutic amount. But why are these bacteria there? Right? Why are they present? Right? Is it just so like, you eat some fiber, bunch of beans? Right? You ever wondered that? Right? One of my favorite movies. Oh yeah, it's one of my favorite movies, but I can't even think of what the heck it's actually called. Blazing Saddles. Right? The part where all the cowboys are sitting around the fire eating beans, and they're just all farting around, and the head guy comes out, and somebody asks him if he wants some beans, and you just hear all these cowboys farting. Well, why does that happen? Right? And it has to do with fiber. Right? As I had mentioned previously, in our intestines, right, there's all this bacteria, and the purpose of this bacteria is to ferment certain food products. For instance, the insoluble fiber. That fiber which the enzymes can't break down, the bacteria can. The bacteria can produce vitamin K, for instance. It can produce certain fatty acids like butyric acid. But when it does this, one of the byproducts is gas production, right? Kind of methane, and hence the reason why, beans or any high fibrous food can cause increased flatulence. Right, cruciferous vegetables, for instance, they have a much higher level of fiber in them, especially insoluble fiber. And again, as the bacteria ferment them, they then produce this gas. Sometimes it's noxious gas. Depends. If you just went to Taco Bell, that's enough to take out a whole block. Right, that stuff is potent. So the bacteria in the intestines, they are absolutely 100% necessary. Right? The reason why they are there. So for the reasons I just discussed, but the other part, or the other reason they are necessary, they're there to prevent the pathogenic growth of certain bacteria. Right? Even healthy, normal, helpful bacteria, if they're overgrown, that's a problem. Right? They can potentially cause a problem. Right? It's I always go to this analogy, I always kind of go to this statement, right? Same thing with inflammation. A little bit of inflammation's really good. A little bit more, totally fine. Too much, that's a bad thing. Same thing with healthy bacteria. A little bit, good. Normal amount, awesome. Too much, that's a problem. I always talk about cake. Eating a piece of chocolate cake, that's a good thing. Eating 2 pieces, even better. Eating a whole chocolate cake, that's a problem. Right. So, when I say pathogenic, even, for instance, C. diff, Clostridium difficile, that is right, if that becomes pathogenic, people can develop a C. diff infection. And if you've ever smelled C. diff stool, right now you're like probably snorting, you're not snorting, you're probably like just blowing air out of your nose and just envisioning, right? You can smell what that is. But my whole point is C. diff, that is a normally occurring bacteria. Right? That is normal. That is already present in the intestine. People who are immunocompromised, for instance, people whose immune system aren't functioning up to snuff, whether they have some sort of autoimmune condition, cancer, treatment, whatever it happens to be. So when that happens, the flora, or the bacterium within the intestines, have difficulty regulating the bacteria in the intestine, right? That's part of where the lymphoid tissue comes into play. That lymphoid tissue helps to prevent that pathogenic bacteria from flourishing, that prevents infection from setting in. Right? But the whole point with C. diff is it's a happy, healthy, not happy, healthy, but it is a normally occurring strain. So just because someone has developed a C. diff infection doesn't necessarily mean, these people, weren't being, cautious and they spread it from a different patient. Not necessarily, right? It's a normally occurring strain. So if somebody is already immunocompromised, they themselves, their own immune system, may have just lacked the ability to keep that under control or under regulation. So here, the Peyer's patches, right? These, we see these in the ileum, right? In the ileum specifically, right? There is lymphoid tissue throughout, but these large bundles of lymphoid tissue, again, those we see in the ileum. So great, we've gotten through the small intestine from the standpoint of looking at some of the differences. Now we are going to look at kind of the last straw, or that last line of defense, right? Because that's really kind of what the wall of the intestine is, right? We want to make sure that nutrients, molecules that are able to get into the body, we want to make sure that they do. We also, at the same time, want to make sure that molecules, toxins, chemicals that aren't supposed to get into the body, we want to make sure they don't. Right? That goes back to when I first began talking about digestion. Right? That has to do with just because something is in the intestines, technically it's not inside of the body. Right? You've eaten it, it's gone to your stomach, it's gone to through your intestines, but anything that's in the intestines is going to essentially be eliminated through the stool. So if it remains in the intestines, you never absorbed it. So we need to ensure that we can absorb these different molecules. So as one of the ways to, again, heighten that quote-unquote security, if you will, along with one of the ways to maximize the digestion and absorption, is along the microvilli. Again, that's what these little, kind of fingers here represent. Right? This is one intestinal cell. These are all microvilli. The microvilli produce something called the brush border. Right? The brush border is just laden with different bacteria. Laden with different enzymes. Right? Lactase, maltase, right? Sucrase, different enzymes which can help further break down the food that we're consuming. Right? You can see monosaccharides at the top, up in here. Right? The monosaccharides. Monosaccharides are a simple sugar, right? Mono 1 saccharide sugar. Yeah, it's a single sugar. That's where you see glucose, right? Glucose, galactose, fructose, right? Those are the three. Those comprise 98% of the simple sugars, or the monosaccharides, which exist. And we have to make sure, right, when we talk about simple sugars, you got to avoid white bread. You can't have Wonder Bread, it's just a simple carbohydrate. What's wrong with you? Yeah, when we talk about simple sugars, right? Table sugar, brown sugar, for instance. Right? Brown sugar is a little less, white sugar is a little more refined. But when we talk about table sugar, for instance, right? That's just simple molecules of a combination of glucose and fructose. Right? That's what's called a disaccharide. It's not a simple sugar, but it is a pretty simple sugar. Right? It's called a disaccharide, which is only two, a chain of two. That's it. Fiber. Right? Fiber is made up of thousands of chains of these different sugars. So when I say, a disaccharide or table sugar isn't a simple sugar, I mean, for all intents and purposes, I mean, it is quite a simple sugar compared to that of fiber, for instance. When we talk about complex carbohydrates, you gotta eat whole grains. What's wrong with you? Man, how dare you not eat a whole grain roll with your whatever? If you're gonna eat pasta, if you're gonna eat a giant bowl of pasta, at least you can do is eat a whole grain pasta or whole wheat pasta. Right? Whole grain roll. You gotta eat a whole grain roll. You can't just have a plain old white bread. Whatever it is, right? The reason why people talk about, complex carbohydrates is because of the size of them and the what it takes for your body to break down that complex carbohydrate. It takes a significantly greater amount of time for your body to break down that complex carbohydrate. Right? If a complex carbohydrate had the chain as thousands of different saccharides in its chain, we can all envision how it would take a much, much longer period of time to absorb those sugars or those saccharides, much longer than if we just ate spoonfuls of white table sugar, which is only 2. Right? Complex carbohydrates are hundreds and thousands in length. Simple sugars are 1 by themselves. Disaccharides like table sugar, right? Lactase, right? Malt, right? Maltose. They're also, right, disaccharides. So they're not simple sugars. However, they are. I mean, they are very, right. They are. Simple sugars are one single sugar molecule, right? But even being disaccharide, they're very simple compared to that of complex carbohydrates. So my whole point with that is we've got to break these molecules down so they can fit across this intestinal wall. If they're very large, they're not going to fit through. Right? Sonic, before it closed near my house, God bless its heart, they used to have milkshakes. They still do, but not the one that's near my house. It closed. But they had these fresh banana milkshakes. Oh, then after 8 o'clock, they were like half off. Like I've contemplated driving like 45 minutes to the closest Sonic just for this thing, but I haven't. Maybe I'll do that tonight. You know, damn it, I'm doing it. It's happening. Anyways, these fresh banana milkshakes, right? You would be drinking the milkshake, and all of a sudden you'd get a chunk of banana stuck in it, and you couldn't get that chunk of banana through. That's the exact same process or the exact same concept as these complex carbohydrates. They have to be broken down in order to be able to fit through the intestinal wall. If they're too large, they can't be absorbed. They don't do the body any good. They do a minimal amount of good. Right? The bacteria in the intestines can continue to ferment them for sure, but really they don't do much good. And so one of the things we see, glucose and galactose, secondary active transport with sodium. Yeah, one of the things with, right, diffusion. I know I've talked about diffusion before. Good God, right? I wish this man would move off of diffusion and stop talking about it, but I can't. It's just too damn important. There's so many things inside of the body which revolve around diffusion. Right, diffusion. When molecules go from an area of high concentration to low concentration. It takes no energy. I set a ball on the top part of a hill. I let it go. It rolls down the hill. Right? I set a toy boat in a stream, and the current of the river takes the boat downstream. It takes no energy whatsoever. The problem with that, though, is it only occurs until both sides are equal. Right? If there were, right, 10 molecules of glucose on, you know, this side of the intestinal wall, let's say there were none on the blood side. Well, equilibrium, or I'm sorry, simple diffusion would make it so 5 would cross until there were 5 on the blood side or the capillary side, and 5 would remain in the intestines. There's equilibrium, no more glucose would cross over. That's a problem. Glucose, we want to absorb as much glucose as humanly possible. Everything utilizes glucose. Every living thing on this planet utilizes glucose, except one virus we found. No, it's not COVID-19. I forget what it is, but yeah, it actually doesn't utilize any ATP, which is fascinating to I'll get up. Anyways, I'm digressing on something that's not that interesting. But with our own body, right, we want to absorb as much glucose as possible. So simple diffusion isn't going to cut it. That's not going to work. Here, right, with glucose, galactose, via active transport. Again, active. If it's active transport, that means we are going to expend energy in order to absorb as much of that glucose as possible. That means glucose can be pumped against its concentration gradient. The hell does that mean? If you remember, right? Remember, if there's 5 molecules of glucose on this side and there's 5 molecules on this side, no diffusion is going to occur because they're equal. With active transport, because it's a pump, I can take these 5 molecules of glucose that are on this side and I can pump them across the intestinal wall. Therefore, all 10 molecules enter the bloodstream and 0 are left inside of the intestine. Those numbers are completely arbitrary. I'm merely using them as the example. Okay? Right? Fructose. Fructose is a little bit different. Facilitated diffusion. Facilitated diffusion is when it is a form of diffusion which does not require any sort of energy, doesn't utilize any ATP. But facilitated diffusion, there is a carrier, right? Meaning, think about it like piggybacking, if you will, right? So there is some sort of gatekeeper who has to open up the gate and allow fructose to enter into, right? So that's the form of facilitated diffusion. One of the things which will allow fructose to enter into the intestinal cell and into the capillary, there's a whole series of what are called GLUT transporters. Essentially, fructose piggybacks on glucose, and as we absorb more glucose, we therefore absorb more fructose. Next are amino acids, right? Little tiny building blocks of protein. Right? There are large proteins. You eat a steak, you eat a chicken wing, right? Whatever it happens to be. If you use chicken wing, make sure you use blue cheese. Get that ranch nonsense out of here. But the chicken wing, it's got an abundance of protein. Yeah. That protein is a very complex form of, it's basically a chain of thousands of amino acids. Again, just the same as with the carbohydrate, that's way too big to absorb. I can't do it. So we've got to break that protein down into the individualized amino acids. And when we do that, that's where we can then begin to absorb the amino acids. And again, you can see, right? Active transport, right? We want to absorb these amino acids as many of these amino acids as possible into the intestinal wall, right? Then from the intestinal wall, absorbs through into the bloodstream. Short chain fatty acids, again, simple diffusion. The other thing, and I hadn't mentioned it yet, the other thing with carbohydrates, proteins, fats, if you'll recall, right, the plasma membrane of cells, it's composed up of a phospholipid bilayer or a double layer of fat. Fats get along with fats. Remember, talking about the hormones. There was water-soluble hormones. Water and fats don't mix, right? Fill up a pot of water, dump oil into it. They don't mix, right? As I mentioned, if you do this, cooking, don't dump oil in your pasta water. Makes no sense. I mean, it actually deters the sauce from sticking. But when we do this, right, that idea that water and fats or lipids don't mix, water-soluble hormones, if you remember, they had to bind to a receptor on the plasma membrane. They could not actually enter into the cell. Right, so they bound to a receptor on the plasma membrane, and that set off a whole cascade of different protein kinases, right, which were the workers within the cell, which made the change. Lipid-soluble hormones like any of the sex hormones, testosterone, estrogen, progesterone, cortisol, right, they were all lipid-soluble hormones. Well, fats like fats. Hey, you're a fat, I'm a fat. Come on over, hang out, let's do this. Well, not now. We're under quarantine. You're 6, gotta keep 6 feet. But when that's eliminated, when we can all hang out, right, the fats like to hang out with fats. So those lipid-soluble hormones can travel through that fat-based membrane, right, that plasma membrane. And those lipid-soluble hormones can actually enter into the nucleus, bind to the receptor, and then from there, it can cause the different proteins and ribosomes to be produced. Same idea here with these fatty acids, right, especially these short-chain fatty acids. You can see these short-chain fatty acids just via simple diffusion. I'm a fat, all right, I'm just going to allow myself to enter into the cell, and from there, enter into the bloodstream. Large-chain fatty acids, right? Large-chain fatty acids, we can see, simple diffusion. One of the things with large-chain fatty acids, right, again, triglycerides, right? Triglycerides is also the same thing as triacylglycerol. Right, they're two different terms, but they are the same thing that we are talking about. Triglycerides can't just, we don't want triglycerides just hanging out in the blood, right? There are, triglycerides are present in the blood, but they need to be regulated. Most triglycerides are piggybacked onto a protein, they're called lipoproteins, or something called cholesterol. There's different types of cholesterol. We'll talk about those in a little bit. But one of the things with these large chain fatty acids, right, is they don't actually enter into the bloodstream. We see here to the lacteal of a villus. Yeah, these large chain fatty acids are actually going to dump into the lymphatic system as opposed to the bloodstream. So we can see, right, here is all of the different villi. Right over here, we can see the bloodstream, the capillary bed, this network of capillaries in the villi. Again, different nutrients, glucose, galactose, soda, whatever it happens to be. Right, these proteins, carbohydrates, small chain fatty acids enter directly into the bloodstream. Right. Large chain fatty acids, these green vessels here, those are lacteals. Right? Those actually allow for the large chain fatty acids to enter into them. Now, one of the reasons why that happens, actually I forgot the part of the large chain fatty acid entering into the lacteals. We're actually going that's about make it about 3 slides. I forgot I'm first going to begin with the proteins, the carbohydrates, short chain fatty acids. So the vast majority of what you eat, as it gets absorbed, it enters into the bloodstream. Now you can see it doesn't matter whether it's the small intestine, large intestine. You can see not all vessels, right, of the circulation are present. Right, we can see that the small intestines, which would be here, have been removed, so we can see all of these different mesenteric vessels. But just understand that all of the vein, all this entire capillary network of veins, these entire large, these venules here, the large veins here, all of them combine and eventually feed into the hepatic portal vein. Right, that's a part of what's called the hepatic portal circulation. So we see hepatic portal circulation leads to glycogen, cholesterol, triglyceride synthesis, hormonal degradation, bile production, waste and toxin detoxification. Right? So our liver has all this ability. Right? We talked about it previously a little bit, and I'll talk about it now again. Our liver can adjust the composition of the blood. If we consume too much glucose, or if we consume too much food, right, glycogen or glucose levels are going to elevate. Right? Same thing with triglyceride levels, right? They too are going to elevate. But one of the things that we kind of commonly don't think about, or one of the misconceptions is, like, if I'm having like a pot roast, like a Sunday dinner, right? I don't know why I mentioned Sunday. It doesn't have to be Sunday. Eat pot roast whenever you want. But that fat that's on it, or even a steak, a sirloin steak, all the fat that's on it, right? If you take that, consume that fat, right? It's not like that fat all of a sudden then just is absorbed as fat and goes and gets deposited right in your butt as fat or wherever it gets deposited. The majority of that fat is actually going to be converted into glucose, right? The majority of it is converted into glucose. So even when you even when you consume fats or triglycerides, right, the bulk of that is going to convert it into glucose. Proteins is a little bit different. Proteins, depending on how much you've consumed, right, generally, right, around 30 grams, 40 grams at one time, that's the most that your body is going to convert, or the most that your body is going to divert into muscle synthesis, right? So if you were, I'm intaking 100 grams of protein at one time because I'm eating a shake and a bunch of chicken breasts. I mean, that's fine, but you're kind of wasting a large amount of that protein shake, right? Your body is absolutely absorbing all of the protein. Well, no, not all, not 100%, but your body is absorbing the vast majority of that protein, absolutely. However, if you are someone who's, for instance, drinking protein shakes, obviously you're doing that for the intent of putting on muscle mass. The problem with consuming 60, 70, 80 grams of protein at one time is the fact that only 30, maybe 40 grams at absolute most are getting diverted to muscle synthesis at that time. The rest of it is simply being converted into glucose, right? And depending on what else you've consumed at that time, the excess gets converted into glucose, and then it may potentially get converted into triglycerides as well. So a small apology. I had to pause for a second and deal with an issue. My kid, somebody was murdering somebody. I kind of forgot where I was talking, but I'm pretty confident that I think I remember the glycogen, right? How I mentioned all of the nutrients we consume, right? They get absorbed into the bloodstream, and then from there they enter into the liver, right? And so all the things we just talked about, as far as the liver's ability to, right, produce glucose, or well, it can produce glucose, but how I was talking about, if you had just consumed a huge abundance of proteins, right? Only around 30 to 40 grams of those proteins actually are diverted towards muscle synthesis. The rest are converted either into glucose or into triglycerides, right? And the cholesterol, we touched on it earlier, right? Your liver produces cholesterol in conjunction with the diet, right? Depending on if you consumed low levels of cholesterol via the diet on one particular day, your liver makes less cholesterol that particular day, right? The next day, if you eat a lesser amount of cholesterol, your liver makes a greater amount, right? So let me see, hormonal degradation, synthesis. Yes, certain hormones are produced in the liver. At meantime, the liver is able to break down certain hormones, right? Many hormones actually get metabolized in the liver, because remember, as we only want hormones to be present in the need that they need to be present, right? For instance, if a certain hormone like antidiuretic hormone, if that were just continuously present in the bloodstream, right, that would cause us just to continuously retain more and more and more and more and more fluid. That would elevate our blood pressure. That's a problem. Right, so one of the ways is to begin to break down these hormones. So as the liver breaks them down, right, that hormone no longer has any sort of impact or effect. Bile production, this we covered in great detail in the previous presentation, so I'm not going to cover this here. Waste toxin detoxification, right, same thing. So we see, why does it make sense for nutrients that you just absorbed to immediately travel to the liver? And that has to do with the fact that, again, in your bloodstream, at a given time, there's around, call it 8-ish grams of glucose. If, hey, I just drank a Coke, or if I just drank some sort of naked juice, or if I just juiced a bunch of, whatever, it doesn't matter what it is. If you just just drank or just ate some, again, let's just call it a soda. All right, so average soda in a bottle, let's say it has around 50 grams of sugar. There's only around 8 in the bloodstream at a given time, so you just ingested roughly 5 times that, 6 times that. So our body has to very quickly and very effectively get that glucose out of the blood. So again, that's the responsibility of the liver. Right? Take the glucose, convert it into glycogen and store it. Or at the same token, take that glucose and turn it into the triglyceride. Now, the other hormone, right, there's many hormones, but the other primary hormone which functions to cause the body to store glycogen or store glucose as glycogen, or causes our body to store triglycerides, that's insulin. Right, remember, insulin is the hormone released by the pancreas in response to elevated blood glucose levels. Right, as glucose levels elevate, insulin elevates and then causes skeletal muscle, right, the liver, the kidneys a little bit. It causes them to store glucose, right, in the form of glycogen. The liver, however, can function independent to that of the pancreas. meaning hepatocytes or liver cells, they don't need insulin in order to absorb and store glucose. They don't have a receptor for insulin because they don't need it. Right? They function independent to that of insulin. That's much different than skeletal muscle cells. So here is where we are going to look at, again, the absorption of large chain fatty acids. Right? How I mentioned, these are going to enter into, right, the lymphatic system via these lacteals, these green vessels here. Right? These are a part of the lymphatic system. Right? That's going to enter up, it's going to bypass the hepatic portal vein and dump into the subclavian vein it's going to dump into the subclavian vein right here via something called the thoracic duct. Now, there's a few ideas, reasons, a few kind of theories as to why, right, this is. One of them is, right, fatty acids is definitely, right, by far and away the most, right, common or most abundant and utilized fuel source in the body. Right, when we talk about energy production and in metabolism and nutrition, we'll get there. We'll talk about that. But the vast majority of your ATP, right, those energy molecules, arise from fatty acid, right? Arise from fatty acid production, or the metabolism of fatty acids. Even if you're a sprinter, right, the vast majority of ATP will always come from fatty acid, right? The breakdown of fatty acids, and your body utilizing the glycerol head, the conversion of ketones, all that sort of thing. In nutrition and metabolism, we'll talk about that. However, the amount of ATP your body can produce can be increased by both the breakdown of fatty acids, but as well as increasing the breakdown of glucose and utilizing that and turning that into ATP. Right. So when I say, oh, fatty acids are the preferred fuel source, yeah. Right? Certain organs like the heart, right? The heart almost purely, when I say almost, I mean the heart purely utilizes fatty acids, right? The heart muscle, cardiac muscle, has a huge number of mitochondria for that very reason. Other organs, a little different, right? The brain almost exclusively utilizes glucose. Right, so they're not all organs, not all tissues only utilize one or the other, but the body as a whole uses significantly greater number of fatty acids to produce ATP. Right, so the physiologic regulation. Right, here's just kind of an overview. Right, we've talked about all of these things before. Right, we talked about all of these different hormones, from gastrin to secretin, the CCK. We talked about all of these. So if you just kind of one little kind of overview or one slide, think about it. The stomach distends, right? Gastrin is then released, right? Gastrin then causes, increases gastric motility, increases acid production, and so on and so forth. I kind of belabored these processes for in last presentation, this presentation, so I'm not going to look at this again. I'm going to actually just move on. Once the food, or the chyme, right, once that bolus has gone from the intestine, the small intestine, the next course it has, or the next route it has to get into, is the large intestine. And right down through here, there's something called the ileocecal valve, or the ileocecal sphincter. That is the valve which relaxes to allow food to go from the ileum and to dump down into the cecum. Right, the movement of food, the movement of chyme through the small intestine, it's relatively constant. Right. However, one of the things which is going to stimulate the movement of food from the ileum into the colon, again, the colon being the large intestine, specifically this little pouching here, this little outpouching here, this first little pouch of the large intestine is something called the cecum. So when we eat food, that actually stimulates a reflex called the gastrocolic reflex, and that leads to the ileum contracting and essentially sending all of its chyme into that cecum. Because again, if we just consume food, we just ate food, we've got to make more room in the small intestine because food will soon be entering into the small intestine and will need to be digested. So, does the large intestine absorb nutrients? I mean, yes, right? Comparatively so. Comparing it to the small intestine, significantly less, right? Really, the majority of the nutrients have already been absorbed, right? Look at the difference, right? Here's the intestinal wall of the large intestine. You don't see any of these really large villi at all. You don't see that whatsoever, right? Really, the primary means or the primary role of the large intestine is to absorb any additional water which is remaining in the stool. It's not there to absorb all of the water, just simply the abundance of water, right? Because if the intestines, let's say if we have reduced gastric motility, meaning the stool, meaning that the stool is moving through the intestines much more slowly. As that happens, the large intestines can absorb more and more and more water. When that happens, that hardens the stool, which in turn causes the stool to move that much more slowly, which in turn causes the large intestine to absorb that much more water. So it just makes the cycle of constipation that much worse. Flip side, my large intestine isn't absorbing enough water, right? In that token, what will happen is if too much water remains in the stool is liquidy, and that's where we then have diarrhea, right? Certain infections, right? Certain GI infections, certain intestinal infections can cause diarrhea, right? And technically, I guess if you want, however, it might be semantics, but your body is causing itself to have diarrhea, right? There's an infection in the intestines, so your body wants to flush you. If there is something in the hose, you go hook the hose up to the spigot and you flush out the hose. That's the same exact thing that the intestines are trying to do. Leave excess water in the intestines so we can help to flush out the pathogen, whatever it happens to be, right? Same thing with a fever, right? Technically, the virus or the bacteria, whatever, the infection isn't giving you a fever. Your body is giving itself a fever because those bacterial, those pathogenic microbes don't like increased temperature, right? Our body cells like it right around 98.6, right? Guess what? Bacterial cells like that same temperature. So if we crank up the thermostat to 99, 100, 101, 102, yeah, our own body cells start to die, but at the same token, so do the bacterial cells. All right. So, anyways, with the large intestine, again, its primary role, absorb nutrients, predominantly water. Really, at that point, any additional water, right? Produce various nutrients. Yeah, as I mentioned, think something like vitamin K, right? Certain B vitamins, right, can be produced in the large intestine as well. Butyric acid. Butyric acid is a fatty acid, which your heart absolutely loves to utilize as a source of energy. Right. Ferment certain stool products. Yeah, that's one of the ways that is the way that it actually produces the different nutrients, is by fermenting the insoluble fiber which remains within the intestine. So, how do we get the stool? How do we get the stool? How do we get that moving from point A to point B? A couple of things. Something called haustral churning. You see how these little segments, right? There's like one here, another one here, another one here, another one. They're little pouches, if you will. So they're specialized. Think of it as almost like specialized peristalsis, right? Remember, the esophagus, the intestine, all of it goes through peristalsis. But the haustral churning, right? When that happens, the stool enters into the cecum. The cecum then distends, and when that happens, this rope, something called the tinea coli. There's like a big kind of rope of connective tissue. So what happens is as the haustra expand, because of the food or the stool that's inside of them, this one segment contracts and it propels and pushes that food or that stool up into the next haustra. That haustra then distends, which stimulates that haustra to contract and it pushes that stool up to the next haustra. Right? That pulling motion occurs along the tinea coli. Right? That's why the stool can move along the large intestine in the manner, in this segmental pattern that it does. Right, so once, again, peristalsis, we've covered that already. Skip over it. Right, mass peristalsis quickly drives the contents of the colon into the rectum. Well, yeah, right. It's not like stool just like hangs out here in the sigmoid colon in the rectum. No, right. Stool hangs out here in the lower portion of the descending colon, and once get that urge, that defecation reflex, there's a very quick, sudden kind of peristalsis which pushes the stool out of the sigmoid colon. Right now, can somebody have such a blockage or such be so constipated where stool may end up being down here in the sigmoid colon? It can, right, for sure, right. But generally, stool doesn't just hang out down here in the sigmoid colon. So we see, right, as the rectum distends, right, stretch receptors are stimulated, triggering the defecation reflex. Right, this leads to relaxation of the internal anal sphincter and contraction of the rectal muscles. Yeah, the first part is involuntary. Right, that sudden urge. Well, I gotta go. Right, it just hit me. Right, hopefully you didn't just eat Taco Bell or something like that, because if you ate Taco Bell, and if you aren't near a toilet, all hope is lost. Right. So that kind of sudden urge, like, oh, I gotta go. Well, what actually is happening is the internal anal sphincter, this guy here, that is going to relax. As that begins to relax, fortunately, we have something called the external anal sphincter here and here. So this is what we can then clench for. So you get that sudden urge, oh, I gotta go. That's when the internal anal sphincter is beginning to relax, and then you can actually tighten, voluntarily control the external anal sphincter. And it's good, because if we couldn't, we'd just be, defecating everywhere all the time. It just would be, just be horrible. Right. But again, that's why we're able to delay defecation until we can actually then get to the toilet, the tree, or whatever, a buddy's car. That was just once in college, and he deserved it. So anyways, but that's why that begins to occur, right? And eventually, right, this will, right, one of those things where if you're trying to rush to a restroom, where you start to get kind of crampy and achy because you just have to, use the facility so badly. Think about taking a weight and holding a bicep curl for 5, 10, 15, 20 minutes, half an hour, whatever it happens to be. The longer and longer you use that muscle, the more kind of uncomfortable and crampy and achy it feels. That's literally the exact same feeling you're starting to feel as you're trying to delay defecation. Right? It's kind of that same kind of muscle burn you get from the skeletal muscle, which comprises the external anal sphincter. So we can see throughout the digestive process, right, vast amounts of fluid have been utilized. Yeah, from the saliva, right, from all of the different mucus, the gastric juices, the bile, the pancreatic juice, the intestinal secretions. There's huge amounts of fluid which are produced. And you can see virtually all of it's reabsorbed. Right, almost all of it is reabsorbed. Right, if ingesting, secreting around just over 9 liters, 9.3, how much is reabsorbed? Almost 9.2. Right, there's a very small amount of fluid which is lost through the GI tract. Right, a very small amount. Something else, right, when we think about, when we just look at how much bile, how much pancreatic juice, how much intestinal juice, how much of this stuff that's produced, that's one of the reasons, if you've ever noticed, like when you overeat, You just get thirsty. Man, you just get thirsty as all get up. And why? Because when you overconsume food, what's happening? Gastric juice, you can see, there's a huge abundance of it which is produced. Same thing with pancreatic juice. Same thing with saliva. So if I have just consumed a bunch of food, that's going to stimulate the release of an abundance of gastric juice, an abundance of pancreatic juice, intestinal juice. That's fluid which has to be pulled from somewhere. Where is it pulled from? Well, it's pulled from the interstitium and it's pulled from the blood. So what happens when you are starting to pull fluid out of the bloodstream? That stimulates, right, your thirst. Right? So therefore we then get thirsty. And then we want to drink. And then you feel even more full. And the stomach distends even more so. Right? It has a lot more to do with the overconsumption of food than it does eating some sort of overly salty food. Right? Generally, when we think about like overly laden, overly salty foods, French fries, burgers, those sorts of things. I hate to always talk about burgers and fries, but 40% of the meals eaten in this country are cheeseburgers and French fries. Yes, you heard that correctly. Right? Almost half. Right? So there's a huge number. Right? That comprises a huge amount of our diet. Right? So that's why I always talk about it. Because it's not just like, oh, one example that we consume once in a while. No, it is something that the average American consumes on almost, right, I say almost daily, not quite daily, but 5-6 times a week, right, whether it's lunch, whether it's dinner. So anyways, my whole point to this, that's another one of the problems with overeating, and that's the reason why, geez, I just feel so darn thirsty after I just eaten so much.